Okay, so last class we discussed about that analog to digital conversion and digital to analog conversion. Basically, I am interested about the sampling frequency, concept of sampling frequency and quantization, and also we discuss about the memory requirement for store a digital signal. It may be a one dimensional signal, it may be a multi-dimensional signal. So, both the cases we have done that. Today, we talk about the concept of frequency in continuous time and discrete time signal. So, continuous time and discrete time signal, basically we talk about sinusoidal signal. So, what is the concept of frequency, discrete frequency, analog frequency, all kinds of things we will talk about. Let us consider for the analog sinusoidal. So, I can write down an analog sinusoidal XAT. So, XAT is nothing but a cos omega t plus theta. This omega is analog frequency, that means the radian per second, and theta is the phase and t is the continuous time. So, now if this is my signal, then I can say for every fixed value of the frequency f. So, what is omega? Omega is nothing but a 2 pi f. This f is called analog frequency, which is radian per second. So, for fixed value of the frequency f, xt is periodic. What is the meaning? Suppose I said I want to generate a 200 hertz sinusoidal signal. So, I said f is equal to small f is equal to 200 hertz. Okay. Now, what should be the analog frequency? What should the signal? So, XAT should be a cos 2 pi into 200 t plus theta. So, I can say, so in that case, if the frequency f is 200, then what is the period t? T is equal to 1 by 200 second. Now, if I change the frequency f to 400, then the period also will be 1 by 400 second. So, for every fixed values of the frequency f, the xt is periodic, whose period is 1 by f. Is okay? So, continuous time sinusoidal signal with distinct frequency are themselves distinct. So, if I said a cos 200 hertz cosine wave and 400 hertz cosine wave, they are two distinct. So, they are distinct. So, if I say, already you have learned about the Fourier transform. So, when I say cos 200 hertz and if I turn the frequency transform, if this axis is my f, then I get a peak at 200 hertz. Now, when I converted the 400 hertz, I get a peak at 400 hertz, and those two peaks are distinct themselves. They are not overlap in nature. So, continuous time sinusoidal with distinct frequency are themselves distinct. So, XAT with 200 hertz and let us say X1AT is 400 hertz, they are not equal, they are distinct. Increase the frequency result in increased rate of oscillation. So, if I say I take a 200 hertz sinusoidal signal, so it will look like this. Now, when I take the 400 hertz sinusoidal signal, then within a half period, there will be a complete sinusoidal signal will be there. So, if I see, if I increase the frequency, so number of oscillation will be increased per second, because t is decreases. So, how many oscillation will be 1 second if the frequency f is equal to 200 hertz? So, 200 hertz frequency means t is equal to 1 by 200 hertz second, 1 by 200 second, that is t. So, in 1 second, how many oscillation will be there? I can calculate number of frequency, that is 200. Similarly, when I say 400, f is equal to 400, then 400 complete period will be there within 1 second. So, if I increase the frequency, rate of oscillation will be increases, more number of period will be increases within 1 second, or I can say the period will be less, t will be decreasing. If frequency is increasing, t is decreasing. Okay. So, there is a three property for a continuous time sinusoidal signal, the frequency concept. One is, for every fixed value of the frequency, xt is periodic, yes, I can calculate. Continuous time sinusoidal signal with distinct frequency are themselves distinct, yes. 200 Hz signal is not overlap with 400 Hz signals, they are distinct. And increase the frequency means rate of oscillation will be increases. So, that is the concept of frequency in a sinusoidal signal. You know that when I say, let us say these two signal, one signal is look like this, another signal is look like this. If I ask you which one contain high frequency component, so what is frequency? More variation, more oscillation will be increases. So, if I see here more oscillations are there, that is why this contain the high frequency component compared to this signal. So, that is the concept of frequency in a sinusoidal signal. Similarly, if I told you what is the concept of frequency in an image, suppose I say white board like this, PPT, white portion. If this is completely white, there is no change in the pixel, then I said it is totally DC, no frequency component. So, when I say no oscillation means my signal will be look like this, no oscillation, signal is constant. So, it is DC signal. Once I include oscillation, once I include variation, then only oscillation will come. So, in case of an image, if it is completely white or completely black, so there is no only DC. Now, once I make some oscillation, suppose here, when there is a change in boundary, so there is a change in pixel colors, so there is some frequency here, there frequency is introduced. So, high frequency means more variation, low frequency means less variation. So, that is the concept of frequency in analog signal. Okay? Is it clear? So, now I go for the digital signal or discrete signal. I said discrete signal. So, what is a discrete signal? Suppose I said I have a signal XAT, let us the same example, which is A cos omega t plus theta. I want to discretize. So, time, discrete time, let us say discrete time, discrete value means A will be quantized, discrete time means t is quantized. So, what should be the discrete signal of XAT, which is nothing but represented by a x of n. So, once I want to do the discretization, what parameter I required? I required a sampling frequency. So, what is sampling frequency? Means after what interval I am collecting the evidence of the analog signal, or I can say what is the resolution of time axis, that I have to know. So, I can say continuous time is represented by n into capital T. Capital T is the difference or distance between the two samples. So, suppose I take this sample and this sample. So, this distance is T, next distance is also T. So, who determine the T? Sampling frequency determine this. So, I know T is equal to 1 by Fs. So, when I discretize this analog signal, I can write down A cos omega, instead of T I write Nt plus theta. So, when I write down Nt, what is capital T? Is nothing but a cos, what is omega? Omega is nothing but the 2 pi capital F. So, capital F denote the analog frequency into T. T is nothing but a 1 by Fs into n plus theta. So, this f by fs is called normalized discrete frequency denoted by small f. Normalized discrete frequency denoted by small f. Okay? Now, this 2 pi into small f we write down by this omega, not this. This omega is analog, this omega is normalized discrete frequency. So, when I say normalized discrete frequency, that means radian per samples. Since it is divided by fs, then it is called radian per sample. So, I write down this is a cos omega t, omega into n. There will be no t, n is the index of the sample plus theta. So, this omega is discrete, normalized discrete frequency, which is nothing but a f by fs. Is it clear? So, due to the sampling, when I write down a discrete signal, it is nothing but a 2 pi f by fs into n plus theta. So, which is nothing but a cos omega n plus theta. So, when I say discrete frequency, xn discrete signal, discrete sinusoidal signal. So, I said xn equal to a is the amplitude cos omega n plus theta, where omega is nothing but a 2 pi f, and this omega is nothing but a radian per sample. Is it clear? So, this small f is nothing but a capital F divided by fs. So, it is a ratio. Okay? And when I write capital omega, it is nothing but a 2 pi capital F. Okay? Now, what is the concept of frequency in discrete sinusoidal signal? It said a discrete time signal is periodic if the frequency f is a rational number. Frequency f is a rational number. So, if it is periodic, then f must be a rational number. So, how do I prove it? Let us say, what is a period in a digital signal? So, if I say a sinusoidal signal, I said this 2 point to this point is a period. In term of sample, when I say, let us say there is a n number of samples are there. So, t is time. Now, time is converted to index in discrete signal. So, let us say within this period there is a n number of samples are there. So, instead of period t, I write n, capital N is the number of sample after which signals is repeat himself. So, if n is the period, then x of n plus capital N must be equal to xn, then only n is a period, because signal has to be repeat itself. So, x of n plus capital N should be equal to x of n for all n. Now, if it is that, if I put that, they will change the index n to n plus capital N, and it should be equal to a cos 2 pi f 0 n plus theta. So, from this equation, I put the value of this one, I get this one. Now, when this equation will be true? So, this relation is true if and only if there exists an integer k such that, because this is nothing but a, so a is cancelled. So, I have to prove cos 2 pi f 0, 2 pi f 0 n plus capital N plus theta should be equal to cos 2 pi f 0 n plus theta. When it is possible? When I can say this is nothing but a cos 2 pi f 0 n plus 2 pi f 0 capital N plus theta is equal to cos 2 pi f 0 n plus theta. Okay. Now, when this will be true? when this part must be equal to the integer multiple of 2 pi. You know that cos 2 pi plus theta is equal to cos theta. So, only when 2 pi f0 n should be equal to the integer multiple of 2 pi. So, I can say f0 2 pi f0 n is equal to 2 pi into k. K is an integer. It may be 2 pi, it may be 4 pi, it may be 6 pi, does not matter. So, in that case, I can say 2 pi cancel. So, f0 is equal to k by n. What is k? K is an integer. What is n? N is also an integer, because that is the period, index of that period. So, integer by integer is nothing but a rational number. So, I said a discrete time sinusoidal signal is periodic if f is a rational number. Clear? Next one, a discrete time sinusoidal whose frequency are separated by an integer multiple of 2 pi are identical. Before that, let us give you the back concept in the sampling. What is the concept? Suppose if I have a baseband signal like FM, this kind of structure, if I sample this signal with sampling frequency Fs, so what is the frequency response we have drawn? What is the frequency? So, this is Fs, so this is Fm and this is Fm. So, this is Fm. So, this is 0 to Fm and this is Fm to Fs. So, that is why Fs is equal to twice Fm. If it is not, there will be aliasing effect that we have discussed during the sampling. So, I said a discrete time sinusoidal whose frequency are separated by integer multiple 2 pi are identical. Why? Because I know cos 2 pi plus theta is equal to cos theta. So, whatever is written, so let us say for cos 4 pi n plus theta, that can be written as cos 2 pi plus 2 pi n theta plus theta. So, I can say if it is cos 2 pi separated by 2 pi, then the cos signal will be again returned back. So, how do I prove it? Let us say cos omega 0 plus 2 pi. So, this signal is 2 pi is separation is 2 pi. So, I added the separation 2 pi here. So, I changed the omega 0, add with 2 pi. So, cos omega 0 plus 2 pi n plus theta. So, I can write down cos omega 0 n multiplied by omega 0 n and 2 pi n plus theta. N is an integer, n varies from 0, 1, 2, 3 dot number of sample. So, I can say this product is nothing but an integer multiple of 2 pi. So, I know if the cos signal is separated by integer multiple of 2 pi, the cos signal again come back. So, this is nothing but again cos omega 0 n plus theta. Because I can write down this one cos 2 pi n plus omega 0 n plus theta, which is equal to nothing but a cos omega 0 n plus theta. Because cos 2 pi plus theta is equal to cos theta. Is it clear? So, a sinusoidal whose frequency are separated by 2 pi, omega value is separated by 2 pi. So, I have an omega 1 and omega 2. If the difference is 2 pi, then they are identical signal. So, let us say I give an example. Let us say cos 2 pi by 3 n is one signal x1, another signal is x2 is equal to cos 2 pi added. So, 2 pi by 3, that means 2 pi plus 2 pi by 3. Let us say this is cos 2 pi plus 2 pi by 3 into n is equal to nothing but a cos 6 plus 2, 8 pi by 3 n. So, this signal and this signal is identical, because it can be written as like this. So, if it is written as like this, then cos 2 pi plus theta is nothing but a cos theta again, cos 2 pi by 3 into n. So, I am saying if a signals are separated by 2 pi, the signal will repeat itself. Okay? So, if the signal is separated by 2 pi, then integer multiple of 2 pi, then the signal will be repeat itself. Then what is the variation of the omega 0? Omega 0 varies from minus pi to pi. How? How it is possible? If I told you, let us say cos, let us say cos pi plus pi by 3 into n is equal to how much? Cos pi plus pi by 3 plus n. So, cos pi plus theta is equal to how much? Minus all sin tan cos minus cos theta. Okay or not? So, I am saying that omega 0, if it is separated by integer multiple of omega k is equal to omega 0 plus 2 pi k, then it is omega 0. The signal will be repeat back. But what is the variation of the omega 0? Omega 0 varies from minus pi to 2 pi, minus pi to pi. How it is possible? So, that said, the highest rate of oscillation in a discrete time sinusoidal is attained when omega is equal to pi or minus pi. I have to prove it. So, if we remember the concept of sampling, there is a aliasing. So, what I said, what is aliasing? So, this is 0, this is my Fm. When Fs is less than twice Fm, let this was Fs, then there will be aliasing, overlapping, aliasing. That is called aliasing. So, said if the omega 0 value is greater than pi, let us say omega 0 is greater than pi, that will be aliased with omega 0 which is less than pi. So, why it is possible? Because you know the highest rate of oscillation is 2 pi, because after 2 pi the signal will repeat itself separated by 2 pi. So, 2 pi is nothing but a Fs. So, I said Fs is equal to 2 pi. Now, what sampling theory said? The Fs must be equal to twice Fm. So, without aliasing, what should be the discrete frequency? Normalized discrete frequency F is equal to analog frequency divided by Fs. So, I can say Fm divided by Fs, which is nothing but Fm divided by twice Fm cancel. So, it is nothing but a half. So, if I consider from 0 to pi, it is half. If I consider pi to 2 pi, so 0 to pi and pi to 2 pi, if I consider, so that means it will start from, you can say that as if it is start from 0 to minus pi. So, then it will come at minus half. So, omega 0 is varies between minus pi to pi, or I can say f small f is varies from minus half to half. Okay. So now let us say that it said the highest rate of oscillation in a discrete time sinusoidal is attained when omega is equal to, so I said the highest rate of oscillation will only attain when omega is equal to pi or omega is equal to minus pi. If it is omega is greater than pi, then it will be allied with omega less than pi. How would I possible? So, at omega equal to 0, no oscillation, then that means it is uniform signal. Let us say omega is equal to pi by 8. So, what is the period? So, omega is nothing but a 2 pi f is equal to pi by 8. So, I can say the f is equal to 1 by 16. So, t is equal to 16 sample in one period. Now, if omega is equal to pi by 4, then 2 pi f is equal to pi by 4. So, pi cancel, f is equal to 1 by 8. So, t is equal to 8. So, omega, value of omega 0 can be 0, pi by 8, pi by 16, I can say the f, small f. Omega 0 is pi by 8 and small f, value of small f is 0, 1 by 16, 1 by 8 and if it is pi by 2, it will be 1 by 4, like that, or t will be 16, 8, 4. So, if I say, if I increase omega, omega 0 is increases within pi, 0 to pi, then rate of oscillation is increasing because t is decreasing. So, rate of oscillation is increasing. When omega 0 is equal to 0, the t is equal to infinite because t is nothing but a 1 by f, f equal to 0. So, 1 by 0 is infinite. So, it is an infinite period. Understand? So, when the omega is increasing from 0 to pi, the oscillation rate of oscillation is increasing. The highest rate of oscillation when it is possible. So, when omega 0 is equal to pi, this case omega 0 is equal to pi, that means 2 pi f 0 is equal to pi. So, I can say the f 0 is equal to half. Now, let us say I am increasing further, I am increasing omega 0 further. So, I am increasing 0 to pi is okay. Let us say omega 0 is greater than pi. That means, let us say I take a sinusoidal signal. So, omega 1. So, omega 0 is greater than pi and less than 2 pi. So, I am increasing the omega 0 not 0 to pi, from pi to 2 pi. So, I am increasing omega 0 from pi to 2 pi. Okay. So, I am taking a signal. So, omega 1 is nothing but a omega 0. So, omega 0 varies taking from pi to 2 pi. Let us say omega 2 is another frequency which is 2 pi minus omega 0. So, I can say the omega 2 varies from pi to 0. When omega 0 is equal to pi, that is pi. When omega 0 is equal to 2 pi, that omega 2 will be 0. Okay or not? I am saying, I am taking omega 2. Let us take another slide. So, what I am saying that I am saying omega 0 is varies from pi to 2 pi. I take omega 1 is a frequency which is equal to omega 0, and I take omega 2 is nothing but a 2 pi minus omega 0, because After 2 pi plus omega 0 will be omega 0. That will be distinct. That we already proved. So, within 2 pi. So, it is varies from 2 pi minus omega 0. So, when omega 0 is equal to pi, then omega 2 is equal to pi. When omega 0 is equal to 2 pi, then omega 2 is equal to 0. So, I can say omega 2 is varies from pi to 0. Now, if I write x1 n is equal to a cos omega 1 n, let us say plus theta, theta is you can write or not write. So, it is nothing but a cos omega 0 n plus theta, because omega 1 is equal to omega 0. Now, I say x2 is another signal which is a cos omega 2 n plus theta. So, I can say it is nothing but a cos 2 pi minus omega 0 into n plus theta, which is nothing but a cos minus omega 0 n plus theta, which is nothing but a cos omega 0 n plus theta, which is nothing but x1 n. So, I am saying if my omega 2 varies from pi to, so if it is omega 0 is greater than pi and less than 2 pi. So, when I am increasing omega 0 above the pi, I am seeing that it is again come back to the x1. So, I am saying signal x2n and x1n are aliasing, they are overlapping. They are the same signal and they are overlapping, because they are same, they are not distinct signal. So, I cannot say that omega 0 can vary from above the pi, because they are not distinct, they are come back again within the x1. So, value of sinusoidal which varies from 0 to pi, oscillation is increasing. Now, once I say that it is greater than pi, so when it is pi, then I know the oscillation is maximum. When it is 0, it is again come to the back to the 0. So, as omega 0 is equal to 0 and omega 0 is equal to that omega 2, when omega 2 is equal to omega 0 is equal to 2 pi, then also omega 2 is equal to 0. So, the concept is that a signal oscillation is increasing up to pi, then it start decreasing and it will become again 0 when omega 0 is equal to 2 pi. Now, if you pictorially, I can represent it in a graphically. Let us say this one, again let us say this one. Again I draw the same graph. So, what I said, this is my 0, this is my Fs, and if the signal is aliased, let us say this is Fs is equal to 1 kilohertz, let us say, and my baseband signal is Fm is equal to let us say 600 hertz. So, what is the sampling frequency said? That Fs is, if it is Fs is equal to twice Fm, that means hertz, then there will be no aliasing. So, I can say this is 0 to 600 hertz. Normalized frequency F varies from 0 to pi, because Fs is, when it is pi, that means it is 600 hertz. If it is Fs is equal to 2 kilohertz, 1.2 kilohertz, then this will be the value of pi. Now, if you see, this value will be aliased with this value. So, this value is 600 hertz. So, if I sampled it, so if the signal is sampled by 1 kilohertz, then what will happen? Let us consider cos 2 pi 600 t is my analog signal. That is, f is equal to 600 hertz. This is sampled with a sampling frequency 1 kilohertz. This is nothing but a cos 6 pi n by 5, which I can write. How can I write? Cos 2 pi minus how much? 6 pi by 5 I have to do. So, 2 pi minus 4 pi by 5, then it is nothing but a 6 pi by 5. So, that is nothing but a cos minus 4 pi by 5. So, what is the f? If I say cos 2 pi f, then my f will be 2 by 5. My f will be 2 by 5. Okay or not? So, what is the analog frequency if I convert it? So, f is equal to f into fs. So, I can say it is 2 by 5 into 1 kilohertz, 400 hertz. So, instead of 600 hertz, I get 400 hertz. So, this is due to the aliasing. So, this is nothing but a 400 hertz from this point to this point. So, instead of 600 hertz, I get a 400 hertz signal, because it is aliased. So, that is why we said if omega 0 is greater than pi, that will be aliased with omega 0 less than pi. Is it clear? So, this is the concept of frequency in discrete time sinusoidal. So, please remember this part: continuous time signal, discrete time signal. Here f is analog, f is in hertz, that means radian per second. Here is normalized discrete normalized discrete frequency. This f is in radian per sample. Radian per sample. So, that f is nothing but a capital F divided by Fs. So, frequency can vary from minus infinity to infinity, but once it is sample, it is restricted by pi to minus pi to pi, or normalized frequency can vary from minus half to plus half, because I know that Fs is equal to twice Fm. So, I know f is equal to f by Fm, f by Fs. So, it is nothing but a twice Fm divided by Fs, Fm divided by twice Fm, Fm cancel, it is half. Either it will be minus half or it will be plus half. Okay? So, please remember this part, because always in signal processing we use normalized discrete frequency. So, even if it is given in hertz, you have to convert it to radian per sample. So, this will be used in many ways. When you implement it, if you just consider the hertz, it will not come. You have to modify it to normalized discrete frequency. So, that concept will again will take forward, because this concept will be used in many places of signal processing. Okay? Thank you.